All right, so we're going to start going through these Khan Academies. So we've got this question number 1 here, and they just want us to set up the integral that will give us the volume of a solid whose cross-sections perpendicular to the x-axis are squares. So perpendicular to the x-axis means we're dealing with regular normal integration. So in other words, our dx's are this way, or our cross sections perpendicular to the x-axis make squares. So it's a dx integral. We're looking for the difference in vertical height, so aka normal integration. So this is going to be an easy problem. Our bounds of integration are actually, oh wait a minute, they don't give us the bounds of integration. We have to solve for them. So we need to know where x over 3 is going to be equal to the square root of x. That's not too bad. By squaring both sides, we get x squared over 9 equals x. So that's where x squared minus 9x equals 0. I just multiplied that 9 to the numerator on the other side and then subtracted. And so it looks like my bounds of integration are going to be 0 and 9. All right. Well, now I need to find the area of a square. That's what I need to integrate, the area of a square. The area of a square is going to be the higher function minus the lower function. And that's the, that vertical distance. That's f minus g, higher minus lower. And it's that makes the base of a square in 3 dimensions. So then it's just that squared. All right. Now maybe Khan Academy will mix that up a little bit. Doesn't look like they do. Great. I fully anticipate to make a mistake at least on 1 or 2 of these, so be careful to watch out for them. All right, up next we have perpendicular to the y-axis makes a square. Okay, so perpendicular to the y-axis means now we've got a dy integral. And we're still making squares though. So let's see here, if it's a dy integral, I need to take that expression, x over 2 plus 2, and rewrite it so that it's x equals stuff. And you'll get that by subtracting the 2 over and then multiplying by 2. All right, so that's my function. I'll probably distribute that out when I actually go through the integration. One thing that's interesting about this is there's not actually 2 curves, but remember that the y-axis, where this region stops, is in itself like a second curve. So the way I'm going to find this volume is, let's see here, since I'm doing a dy integral, I'm integrating from 2 to 5 dy. And in dy integrals, it's further right minus further left. That's the f of x minus g of x, or f of y minus g of y in this case. So the function that's further right is actually, well, my function, 2y minus 4. And that's being compared to, or measured against, the y-axis. So I'm actually just comparing that to 0. So once again, that's the difference, that's the dy, or the, how do I say it? That is the vertical distance between those 2 curves, and that's being squared. And there we go. We don't actually need the minus 0. But we're going to start seeing some rectangles. Yes, we are. All right, so this time notice that they're just describing it. They're not actually giving us a picture. So this one still isn't going to be too bad. The thing is, this time they tell us it's a rectangle. It looks like what we're going to have to be concerned with is which of these functions is higher than the other. Because that's going to dictate whether our, let's see here, how do I say it? That's going to dictate whether, what our order of subtraction is going to be, because it always needs to be higher minus lower. Well, I guess let's graph that as best as we can from 2 to 7. I don't really have anything nice I can do between 2 and 7, but one thing I do know is that, well, 2 is a little bit less than pi, and 7 is a little bit greater than 2 pi. So maybe this will give me a clue. I know that regular sine of x would have gone this far, and would have done something like that. Let me put pi actually in the middle. So remember that sine is just a function that's oscillating between -1 and +1 always. So from pi to 2 pi, from a little bit after 2 to a little bit before 7, I'm between 0 and -1. My guess is this is the lower function, but let's find out. So the next one, let's see here, if that's about 3. The next thing I can easily plug in is 4 for the other function. At 4, my height would be 2. In fact, at 1, my height would be 3, which is definitely higher. So I think I know the order now. It must be the 4 minus square root x is the higher of the two functions. It probably has some shape like that. In fact, it does have some shape like that. And you can plug it into a calculator and see why. Or maybe you just remember that from all your algebra too. So anyways, now we know which function is higher. It should be this first minus sine of x. Since this is a rectangle, that might be the base of my solid, the base. One of those little dx slivers being the base. But the height is simply 2x, so we just multiply the height. It's base, that whole ugly thing, times height will give you your integral. Looks like we've got one more. Thankfully, we haven't actually had to find the actual area and do the real integral. Let's see here. This one were squares perpendicular to the x-axis. So it's going to be 3 minus that function, higher minus lower, perpendicular to the x-axis. And it's just going to be that squared from 3 to wherever these meet. And that's kind of the trick, is where do those two meet. So where is log base 2x equal to 3? Well, just remember, where is log base 2x equal to 3 means 2 is the base, 3 is the exponent, and that gives you what? That's how we, rewrite our logarithm expressions. This is a base, this is an answer, this is an exponent when it's written in this form, and so a base can have an exponent which will give you an answer in its other form. So then our bounds of integration are from 3 to 8. And again, higher minus lower. So that gets us through that first assignment. How are we doing on time? We can start the second. Maybe we'll just separate it into a second video.